All right, kind of expanding on correlation coefficient to get into regression with only one predictor. We need to crawl before we run, so let's. Hopefully, this is a little bit of review from your undergraduate statistics class. So, anyway, given paired data, if we have a linear pattern, a straight line pattern, then we can fit the model or fit a model called a regression line to our collection of paired data. So we create something called a scatter plot, which is, again, it's just a picture of our data. We eyeball it to see if it has a linear tendency. If it does, then we consider fitting a regression line. So the regression equation is just y hat equal b0 plus b1x. It's not y, because y hat is a predicted value, not necessarily an observed value. So the regression equation expresses the relationship between our x and our predicted y values. So that's an important caveat. Again, this having a y with a little tilde above it stands for y hat, not y. Notation, kind of think of this as x bar and mu. Remember back when we were studying sample means, we would use the sample mean to estimate mu, the population parameter, right? Well, same thing here. We calculate a B0, which is the intercept of our regression model, and that's actually used to predict beta 0, which is our population intercept. B1 is calculated, that's called the slope of our regression model using our sample data. This is used to estimate beta 1, which is the population slope. So this is our sample model, which is used to estimate, make statements about our population parameters. So if we're looking at the relationship between maybe someone's HDL and their BMI, what would we do? We'd take a sample and we'd want to use our model to make a statement about that relationship for everyone in our population. So first thing, eyeball it. If we were looking at the relationship between the height of a father and the height of the daughter, I would want to look at these red points and kind of visualize this green line if it wasn't there, which it wouldn't be at first, and say, yeah, is there a linear pattern? If there's not a linear pattern, then we don't need to be fitting a linear regression model. But and there's a model out there that would work, it's just not the linear model. But we need to eyeball it and make sure that linearity can be assumed and a linear model is appropriate. Now, understanding the model coefficients, let's say just for example that we have y hat equals 30.3 plus 1.3x. The 30.3 is our intercept. It is extremely important that you understand the interpretation. And I'm pretty picky on interpretations when you're a student of mine. I expect your interpretation to be exactly like mine. I know, it's not cool, but it is what it is. So the interpretation here is when x is equal to 0, the predicted y value is 30.3. This should make a whole lot of sense to you because if I put 0 in for x, multiply 1.36 times 0, I get 30.3, which again, y hat is the predicted value. So no matter what goes right here without the x, this is called the intercept, and the interpretation is always when x is equal to 0, the predicted y value is whatever this value number is right here. The other is 1.36. That's our, well, shoot. All right, moving from correlation coefficient to regression. Doug Darbro? Now let's do it. So assuming we have a linear pattern, we can fit a model to the pattern to be used for prediction, right? Called a regression line. So the first thing we'll need to do is eyeball our data and make sure that it fits a linear pattern. And if it does, then we can create this regression equation called y hat equal b0 plus b1x. Now I'm going to dive into this and explain all the components to you. But essentially what we're doing here is our model is expressing a relationship between x and the predicted values according to this regression model. So caveat here, typically people say, well, it's just y equal b, and it's not. Y in this context is our observed value. Y hat is the predicted value. This model predicts, so we have to use the predicted notation for y. Same concepts in terms of taking a sample information and using it to estimate population. So we use a sample statistic to make an estimate of a population parameter. Think of this as like X bar estimating mu. Back in the context of a mean, a sample mean, making a statement about population mean. In this case, B0 is just our sample intercept. We use that to make an estimate of our population intercept. B1 is our sample slope. We use it to make an estimate of our population slope. So this model is taken from a sample which is selected from our larger population, and we're using it to make an estimate of an unknown model for the entire population. Check for linearity. Pretty much you just do an eyeball test. So imagine the green line isn't there and you've just got a cluster of red points. You kind of visualize a green line, and if that green line kind of represents a straight line, then you can assume linearity, at least for now. So we need to check for linearity because fitting a linear model to a non-linear set of points is not cool and highly, highly, highly not recommended because it just doesn't work.